Hello everyone, this is part of a problem-solving series that would help you prepare for math competitions such as the AMC 10 and 12, the American Invitational Mathematics Examination, the AIME, and other contests and tournaments in the advanced middle school and high school level. In this session, we will be solving a geometry problem from the ARML competition. Here's a view of the problem. Circle omega 1 has center at O, which turns out to be on the circle omega 2. These circles intersect at point A and C, and at the same time we have a point B which is on circle omega 2, such that these three line segments are provided. Compute the area of omega 1. So let's start by drawing circle omega 1. That's our circle centered at O. That's our omega 1, and then we know that center O is on circle omega 2. Let that be a section of circle omega 2. So now these two circles intersect at points A and C. However, we do not know the exact location of point B. Is the point B inside circle omega 1 or is it outside? So let's start with the case where B is outside. So let's suppose this is point B here. We're given that BA is 37, measures 37. BC here measures 7. And finally BO measures 17. But then look at triangle, that's 17. Look at triangle BOA. Obviously, applying the triangle inequality to this triangle BOA, we establish that OA must be greater than 37 minus 17, which is 20. So OA should measure at least 20, but in that case, OA is simply the radius of circle omega 1, and as such B cannot be outside circle omega 1. So therefore this configuration is not the right configuration. So let's draw the picture one more time, but this time with the correct configuration. So we have our circle omega 1, and that's the center of our circle here, O. And then we have another circle omega 2, and it intersects our circle at 2 points, namely A and C. But we just established that B must actually lie inside our circle. So B is somewhere here. So again, we know that line segment BA is equal to 37. BC, this one is 7. And finally BO, this segment here, is 17. So we need to figure out the area of circle omega 1, which basically tells us that we need to somehow calculate the radius of that circle, which turns out to be simply the line segment OA. So once we figure the segment OA, we're pretty much done. So how to find that line segment? We realize that points A, O, B, and C are concyclic points, so let's write that down. We can be reminded of Ptolemy's theorem for the cyclic quadrilateral, but then it turns out we do not know enough line segments. So for instance, we do not know the measure of line segment AC, we do not know the line segment OA, and similarly for OC, which is the same as OA. So we have two unknowns in that case, which that will not help us immediately. Instead, we will apply the following trick. So let me augment the picture, and then so what I will do instead, I will just create a new point D here close to A. So let's call this point as D, such that D has distance 7 from the point O. So in that case, I'm replicating this distance between B and C. So, but why did I do that? So it turns out that in that occasion, the distance DA turns out to be exactly 17. Can you see why? Do you guys realize that OC is an arc which goes through the kind of spans through the radius of our first circle OC, And so in a sense, OA is also spanning that radius. So as such, DA must be 17. And therefore, instead of now applying Ptolemy theorem to the quadrilateral AOBC, I would rather apply Ptolemy theorem to rather quadrilateral ADOB, and therefore what I have is, well, OD times AB plus AD times OB is actually equal to the product of the diagonals OA times DB. So OD is 7, AB is 37 given in the problem, plus AD is 17 by construction, OB is also 17, and finally OA is our radius of the circle omega 1, so therefore I can call it R1. And interestingly, you can also observe that DB is also R1. Can you figure that? Because, well, we know that OA is a radius, and it goes, well, it kind of creates a triangle where it has side length 7, 17, and OA is the third side. In a similar way, you can think of BOD as a triangle with side length 7, 17, and the last one would be the same radius R1. But then we're done. So the sum here would be equal to 548, which is equal to R1 squared. And the question was asking for the area of omega 1. All I do is multiply both sides of this expression by pi, and I get the result 548 pi. So that solves our problem. That's our answer. So hope to see you guys in our next video.